Hello everyone, welcome back. In pre-calculus, we're going to take a much deeper dive into logarithms and learn about all their properties and how we can do algebra and different types of symbolic manipulations using those properties. But for now, in this introduction to logarithms, we really only need one property, and that's what we refer to as the change of base property for logarithms. So what this change of base property does is basically what the name says. It allows us to take the logarithm of one base and change it to any other base that is appropriate for a logarithm. And why we need a property like the change of base property is because if we want to evaluate a logarithm using something like a computer or a calculator, most computers or calculators only have two types of logs programmed into them. That is the common log, log base 10, and the natural log or log base e. So if we want to convert a logarithm of a different base to one of these more useful bases programmed into a calculator, we got to use this formula. And so the formula says if we start with log base b of a, we can convert that to any other base that works, say n, by taking log base n of a and then dividing that by log base n of our old base b. So we think of n as our new base. And so I don't think the proof of this property is really important at the moment, just really knowing how to use it. And the proof also kind of relies on some of those deeper properties I hinted at earlier. So we're going to skip the proof of this property and just assume that it works. But later on, we will verify that it does work by proving it. But that'll be something we do really in a class like pre-calculus instead. So this is the most general way to write the change of base formula. Log base b of a is equal to log base n of a divided by log base n of b. But like I was mentioning, we're mainly using this change of base property to help us convert logarithms to common logarithms or natural logarithms. So it might be worth writing down a couple more times for those situations. So if we want to convert log base b of a to a natural logarithm, we would take the natural log of a, our original input, and divide that by natural log of b, the natural log of our old base. And what would this look like for common logs? Well, our log base b of a would turn into the common log or log base 10 of a divided by the common log or log base 10 of b. What we're going to end up using this change of base property for is helping us solve simple exponential equations. But before we look at that, let's look at an even simpler example of applying this change of base formula to help us use a calculator to approximate a logarithm. So in this example, we're going to take log base 3 of 7 and try to change its base or convert it. And let's go ahead and convert it to a natural log. So that'll be the natural log of the old input 7 divided by natural log of the old base 3. And now these two logarithms are actually the same thing, but this is one that we could punch into any calculator that has logs programmed into it. So the natural log of 7 will give us one number. We divide that by the second number, the natural log of 3, and our calculator will tell us that value because, well, it's hard to work with these values that are not powers of our base. And according to my calculator in my notes, log base 3 of 7, or equivalently the natural log of 7 divided by the natural log of 3, is approximately 1.7712. I recommend you take a moment to try to plug this into your calculator, make sure you're getting that same value of 1.7712. If you're not, then double check your parentheses and make sure you're plugging it in exactly correct. Another way we could evaluate this using our calculator is instead of converting to the natural log for our base, we could convert to the common log, and so that'd be common log of 7 divided by the common log of 3, but that'll still evaluate to 1.7712. All right, everyone, let's go ahead and look at some examples of solving exponential equations. So the first example we're going to start with is trying to solve the equation 2 to the power of x is equal to 10. And the way we're going to eventually do this is using logarithms and that change of base property for our logarithms. In addition to our change of base property for logarithms, we also want to remember that connection between exponential equations and logarithmic equations. So if we have b to the x is equal to a, then that's the same thing as log base b of a is equal to x. All right, so how are we going to use these two tools to help us solve this equation, 2 to the x is equal to 10? Well, the first thing we're going to do is convert our exponential equation into its logarithmic form. And so what is the logarithmic form of this equation, 2 to the power of x is equal to 10? The base of our logarithm is the same as the base of our exponential, so that'll be log base 2. What goes inside of a logarithm is what comes out of an exponential function. So that's going to be our value 10. And then what comes out of a logarithm is our exponent, in this case x, and that's great because x is our variable, the unknown thing we are trying to find. So the exact value of x is log base 2 of 10. However, most of our calculators cannot evaluate log base 2 of 10, so now we have to invoke our change of base formula and convert this to a base that we can evaluate using our calculators. And remember, our change of base formula has a more general formula that can convert a logarithm to any base we want, but we're almost always using natural log as our base. So for this video, I just wrote up that version of our change of base formula. And so if we apply that to this equation or statement that we have here, if we want to convert log base 2 of 10 to a natural log statement, we take natural log of our old input 10 and divide that by the natural log of our old base 2. So log base 2 of 10 being equal to x is the same as saying x is equal to the natural log of 10 divided by the natural log of 2. And now we can punch that into a calculator and let's see what we get. We get a decimal approximation of about 3.32, and this is reasonable if we think about the original equation we're trying to solve. We're trying to figure out what power do we have to raise x to get 10? Well, 2 to the power of 3 is equal to 8, so that's a little bit under 10. 2 to the power of 4 is equal to 16, and that's above 10. So what power do we have to raise 2 to get 10? It's got to be between 3 and 4, and our logarithms help us figure out that it's actually about 3.32. Unfortunately, not all of our exponential equations will be this simple to solve. So let's go ahead and look at some more examples of some more complicated situations. All right, so here we have another example of an exponential equation that we want to solve. This time we're looking at e to the power of 0.6x is equal to 5. And so our process is actually going to be the same, at least to start off with, as our previous example. And so we're going to convert our exponential equation to a logarithmic equation. So what is the logarithmic version of our equation? Well, the base of our logarithm has to be the same as the base of our exponential, so that'll be log base e, but we call that the natural log. What goes inside of our logarithm is what comes out of our exponential, so that'll be the number 5. And what comes out of our logarithm, or what our logarithm is equal to, is an exponent. It's the exponent we have to raise the base to get 5, and that's this number 0.6 times x. Okay, so our goal here is to solve for x, but it's multiplied by that number 0.6. And so if we take that value, the natural log of 5, and divide it by 0.6 or multiply by 1 over 0.6, we'll get x all by itself. And because the base of our logarithm was e, the natural log, we actually now don't need to use the change of base formula. It's already in a format that we can plug into our calculator. So now we can plug into our calculator the natural log of 5 and divide that value by 0.6, and that'll be our approximation for x. And so according to my calculator, x, or the natural log of 5 divided by 0.6, has a decimal approximation of about 2.6824.